Section 4.8, Newton's Method. We finish our material on derivatives with one application of linearization, solving equations that cannot be solved by our algebraic means or by formulas. So for example, we are going to find the root or solution of this equation, cosine x equal x, correct to 6 decimal places. We will use what is called Newton's method, and it is actually the method behind the programming that computer algebra systems or even graphing calculators use to get approximate solutions. As a little example, let's look at the following picture I have here. We've got a function y equal f of x. It's in blue. It is crossing the x-axis at the point r, and we're trying to figure out what is that point. So we're trying to find the root of the function, which means where it crosses the x-axis, which also means where the function f of x is equal to 0. We can start by taking a guess. We can label that as x1. We actually did something like that when we learned about the intermediate value theorem. So then we take that guess and we plug in x1 into our function, and we get a point x1 comma f of x1. And that is on the graph of our function. Then we can find the line tangent to the function at that point. We'll call that tangent line L, and I have that drawn there in red. And since L is a line, it is easy to find its x-intercept, which we're going to call x2. And notice that in this little picture example, it gets us closer to the actual root. If we do this multiple times, the approximations get better and better. So first, we're going to start with the equation for the tangent line, which we saw in the linearization section. Y minus the function evaluated at the point x1 equal to f prime evaluated at x1, giving us the slope of the line, times x minus x1. Back in the linearization section, you would have seen y minus f of a equal f prime of a times x minus a. This is the exact same thing, it's just that a is now called x1. The x-intercept of the line L is x2, according to our graph up there, which means that the coordinate x2 comma 0 is a point on the line. Substituting this into the equation that we just left off with, we get 0 minus f of x1 equal f prime of x1 times x2 minus x1. If the derivative at x1 is not equal to 0, then we can solve for x2. So just rearranging some terms, we can get to x2, the new x-intercept that we have there, is equal to x1 minus the quotient f of x1 divided by f prime of x1. Notice now we started at x1 and now we've moved to x2, so we could keep repeating this and we'll get closer and closer to r. So we take x2 as the next approximation for r, and we repeat the process. We're going to find another approximation, which we'll call x3. And by the same reasoning that we had above, x3 can be written as x2 minus f of x2 divided by f prime of x2. You can see that we can just keep repeating this, and in general, if the derivative at xn is not equal to 0, then any approximation x sub n plus 1 is equal to the previous approximation, x sub n, minus f evaluated at xn divided by f prime evaluated at xn. So let's go look at our example. We want to find the solution to the equation cosine of x is equal to x, correct to 6 decimal places. First, a quick sketch of the two functions y equal cosine x and y equal x. So here you can see I have y equal cosine x in red and y equal x in blue. And when you graph those, you see that they intersect at some point between x equals 0 and x equal pi over 2. We're going to say the point where they intersect is r, relating to what we saw earlier. And if we take a guess as to where they intersect, we'll take a guess of x1 equal to 1 as some place to start with, because at least 1 is between 0 and pi over 2. Next, we want a function f of x to use in our method. So we're going to write f of x equal to cosine x minus x, since finding where cosine x equals x is the same thing as finding where f of x equal to cosine x minus x is equal to 0. So we've got our function, we've got x1. Let's first start by finding x2 by just using what we had up here. So x2, the next approximation will be x1 minus f of x1 divided by f prime of x1. And as we keep doing more of these, we're going to need our function and our derivative, so we might as well just record those. If f of x is equal to cosine x minus x, then f prime of x is equal to negative sine x minus 1. So then x2 is equal to 1, that's what we said x1 was, minus f of 1, so in this case that'll be cosine of 1 minus 1, divided by f prime of 1. So f prime of 1 will be negative sine of 1 and then minus 1. Now something that we have to remember here is that our trig functions, they're always in radian mode when we're doing things in calculus. So just make a note. You want to use radian mode. If you're ever using trig functions and it's not going to be in radian mode, you would have been given something specifically in degrees. But if you're not given that, something like cosine 1 means cosine of 1 radian. So let's break out our calculator, and you just want to make sure that you're in radian mode, and we're going to find out what this is equal to. So first of all, I want cosine of 1 minus 1. So cosine of 1 minus 1. And you're going to get a decimal out of this, and you don't want to round too early. The point is we're trying to get something correct to 6 decimal places, so it might make sense if we go out to, say, the 8th or 9th decimal place. So the numerator here is negative 0.45969769.4. And then divided by negative sine of 1 minus 1. And that's negative 1.8414709.9. And actually, we can go to the 9th place there, 85. So then we'll do our division and then subtract all of that from 1. So 1 minus the quotient 0.45969769.4 divided by 1.8414709.85. And that gives us approximately 0.75036.387. So that's x2. So then we would take this and use that to find out what x3 is. So x3 would be x2 minus f of x2 divided by f prime of x2. So again, using the same functions, f of x and f prime of x, just like I did with 1, but now with this decimal for x2. And what you're going to get for x3 is 0.7391129, also rounded to 8 decimal places. So as you keep doing that, you'll get x4 approximately 0.73908513, and then x5 will be approximately 0.73908.513. And you can notice that since we just started to repeat ourselves, we're already done. So just after a couple of steps, we can see that the root is approximately, and since we only needed 6 decimal places, 0.739085. We already had rounded to 8 decimal places equal with x4 and x5. But we can just say, rounded to 6 decimal places, that's approximately our root.